Hello everyone, I am Dr. Smriti Tripathi from Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. This video lecture is for Mathematics 4 for the code KAS 302 or 402. Today's topic is Partial Differential Equations, and in that we will discuss equations reducible to partial differential equations with constant coefficient. Now the question arises, what is a equation which is reducible to partial differential equation but cannot be solved by the normal methods? So let's understand this. An equation in which the coefficient of the derivative of any order, say k, is a multiple of the variable of the degree k, then it can be reduced to partial differential equation with constant coefficient. For that, for better understanding, let's see these two examples. In first example, I have written x square r minus y square t plus px minus qi is equal to log x, and in the second example, I have written x square del 2z upon del x2 minus 4xy del 2z upon del x del y plus 4y square del 2z upon del y2 plus 6y del z upon del y is equal to x cube y to the power 4. First, I will explain to you this second equation. You see very carefully, here we have the derivative of z with respect to x, and this derivative is of second order derivative. And please see very carefully, because this is a second order derivative of z with respect to x, and the multiplication of here is of x square. It means the coefficient of del 2z upon del x2 must be in x, and the degree of x must be the same as the order of the derivative. And now similarly, see here, we have a derivative del 2z upon del xy. This means this is the second derivative of z with respect to x and y. That is why the coefficient here is x and y both, right? Similarly, here in this third term, we have the second derivative of z with respect to y, and we have the coefficient as y square. And now see the fourth term, here we have the derivative of z with respect to y, and it is only first order derivative. That is why the multiplication, the coefficient here is a multiple of only y, not y square. So this is a very important point to notice, that wherever we have second derivative, we have the coefficient which is in power of 2, and wherever we have first derivative, the coefficient has only power 1. So this is very important. When we see this kind of equations, we should immediately think that, or we should immediately understand that this kind of equation is reducible to PDE. Alright. Now you can say that there is another equation, and which is in different terms. So you must know, because we are studying PDE, and when we start PDE, at the same time we always explain that P is equal to del z upon del x, Q is equal to del z upon del y, R is equal to del 2z upon del x2, S is equal to del 2z upon del x del y, and T is equal to del 2z upon del y2. We all know this very well, because we are doing partial differential equations. So you see in this example here, if we talk about R, what is it? it is nothing but the second order derivative of z with respect to x, and that is why here we have multiplied by x square. Similarly, in the second term we have t, which is a second order derivative of z with respect to y, and here the multiplication is with y square. It means the coefficient is y square. In the third term p we have, so p says nothing but del z upon del x, and if it is del z upon del x, so the coefficient is x only. And similarly for q also, what is q? Q is del z upon del y, so the coefficient is only y. Now the question arises, how to solve these kind of equations. So what do? We take small x, here we choose small x is equal to e to the power capital X, and small y is equal to e to the power capital Y. So now if small x is equal to e to the power capital X, so obviously capital X will be equal to log x and capital Y will be equal to log y. Now what do we want? We want to reduce our equation into PDE with constant coefficient. It means anyhow we want to reduce or we want to remove this x square. Remove, or you can say we want to transform it in such a form that there should be only some kind of derivative. That's what we wanted. Okay. So on differentiating z partially with respect to x, what do we get? Obviously we will get del z upon del x. Now we want to convert this x into capital X. So how can we write? We can write del z upon del x into del capital X upon del small x. We know that capital X is equal to log x. So on replacing capital X by log x here only, so on replacing it here, we will immediately get the derivative of log x with respect to x. So we will get 1 upon x into del z upon del x. And so we will get x into del z upon del x is equal to del of z upon del of capital S. Let us say this is equation number 1. So if we see this equation very carefully, we will get x into del upon del x is equal to, or we can say it is equivalent to del upon del of capital X, because here the only, so same operation is being done. So hence small x del upon del of small x is equal to del upon del of capital X, which is nothing but equal to capital D. So as we know that we are used to write del upon small x is equal to capital D and del upon del of small y is equal to D dash. So similarly we have changed this into del upon del of capital X. So again we will assume it as capital D. Now again on differentiating equation number 1. What is equation number 1? Equation number 1 is this: x into del z upon del x is equal to del z upon del of capital X. So again on differentiating this we will get del upon del x into del z upon del x is equal to del upon del x in bracket mein, within the brackets 1 upon x into del of z upon del of capital X. Now you see this will convert into del 2 z upon del x2, and here we see very carefully there are two functions. So whenever we differentiate two functions which are in the product form, then we have to apply product rule, and this will become del of del x into 1 upon x. So here I am applying the formula of d u v, which is equal to differentiation of u into v plus u into differentiation of v. So we all know that this is a property of differentiation for product of two functions. So the same property I have applied here. Now when I will differentiate 1 upon x, we will get minus 1 upon x square, and this will remain as it is. Now plus 1 upon x will remain as it is, and we will get the differentiation of del of z upon del of capital X with respect to del upon del of x. Now we have here in the LHS del 2z upon del x2, which is equal to minus 1 upon x square del z upon del of capital X plus 1 upon x del upon del of capital X into del of z upon del of capital X. Now see, here we have to pay attention how we got this. We know that here we have a small x and this is a derivative with respect to capital X. So the differentiation is not possible. Differentiation is only possible if we change this variable as we have the this del z upon del of capital, means we have to apply chain rule here. So this is del upon del of capital X into del z upon del of capital X into del of capital X upon del x. We now know that small x is equal to e to the power capital X. Hence capital X is equal to log x. Now again, on putting capital X is equal to log x here, what do we get? We will get del 2z upon del x2 is equal to minus 1 upon x square into del z upon del of capital X plus 1 upon x del upon del of capital X into del z upon del of capital X and del of log x upon del x. We know that this del of log x upon del x is equal to 1 upon x. So we will get this expression that del 2z upon del x2 is equal to minus 1 by x square del z upon del x plus 1 upon x del upon del x into del z upon del of capital X into 1 upon x. Now see, we got 1x square here, and here also the next term also have x square in the denominator. So now this term which is in the denominator of both the terms, we will take it in the LHS, and so now del 2z upon del x square is equal to minus 1 upon x square del z upon del of capital X plus 1 upon x into del 2z upon del capital X square. And so we will get x square into del 2z upon del x square is equal to minus del z upon del of capital X plus del 2z upon del of capital X square. In the next step, we will get x square del 2z upon del of x square is equal to minus dz plus d square z. Here this d refers to del upon del of capital X. And so we will get x square del 2z upon del x2 is equal to d into d minus 1z. So this way we can say that x into del z upon del x is equal to capital D of z, and we can write x square into del 2z upon del x2 is equal to capital D into capital D minus 1 z, and so on. We can write for x cube del cube z upon del x cube is equal to d minus 1 d minus 2 z, and we can write it up to n term by square. Now as we did for x, similarly if we differentiate z partially with respect to y, we will get this one value, and here I have written d dash because earlier it was capital D. So if we are doing it for y, we will write d dash. All right. Similarly for y square del 2z upon del y2, we will write d dash minus 1 into z, and so on. So you can see for x we will write capital D, and for y we will write capital D dash, and similarly for here xy del 2 z upon del x del y, we will get dd dash into z. Now for reducing our equation into PDE with constant coefficient, we will substitute these values in the given equation and we will get a new equation which is phi dd dash z is equal to v, where v can be any function because it is in the RHS. So now this equation has been converted to PDE with constant coefficient. Let us understand this example. Here the question says solve the linear partial differential equation, and the equation you can see contains second order derivatives as well as first order derivatives. In the first second order derivative, the multiplication here is it with x square. So if the multiplication is with x square, there must be the derivative of with respect to x. So see very carefully, derivative is also with respect to x and the coefficient is x square. Here the derivative is with respect to x and y, second order derivative it is with respect to x and y. So the coefficient is also x and y. Here you see the second order derivative is with respect to y. So we have the coefficient y square, and in the last term we have first order derivative with respect to y. So the coefficient is with y only. Now let's once again assume, as I have already discussed the procedure, we assume small x is equal to e to the power capital X and small y is equal to e to the power capital Y, so that capital X is equal to log x and capital Y is equal to log y. And obviously we get capital D is equivalent to del upon del x and capital D dash is equivalent to del upon del y. So we know that wherever we have second order derivative, we write dd minus 1. If we have this derivative, we write dd dash, and if we have second order derivative with respect to y, then we write d dash into d dash minus 1. It means we replace these values in the question. Whichever terms we have in the equation, we replace these terms by this d minus 1, d dash, d dash minus 1, we replace by these values, alright. So on solving this, we get d square minus 4 dd dash plus 4 d dash square and minus d minus 2 d dash. Again on solving, we get d minus 2 d dash into d minus 2 d dash minus 1 into z is equal to e to the power 3x plus 4y. First of all, we see this equation, and after that we will see this equation. Now we can find its auxiliary equation very easily. Its auxiliary equation will be d square minus 4 dd dash plus 4 d dash square minus d minus 2d dash is equal to 0. Now we know that this factor is d minus 2d dash whole square minus d minus 2d dash is equal to 0. On solving, we get d minus 2d dash into d minus 2d dash, and this will give us minus 1 is equal to 0. So this is the auxiliary equation which we have, and we got the two factors. So we always know how to write the complementary function. Now please keep it remember that this capital D is for capital X and this capital D dash is for capital Y. So whenever we will write complementary function, we will not write small x and small y. We will write capital X and capital Y in our complementary function. So according to the first factor, complementary function will be f1 capital Y plus 2 into capital X, and for second function factor we will write plus e to the power capital X into f2 capital Y plus 2 of capital X. And we also know that capital Y is what? Log y. So we will replace it here. Capital X is log x. So, we will write capital X is equal to log x, and here also. So, on writing it here, you see we know that log m plus log n is equal to log m into n, and log m minus log n is equal to log of m upon n. So, now you see here we will get log y into x square plus x f2 log again y into x square, because we also know that m log n is equal to log n to the power m. So, this 2 log x will become log of x square, and then on applying the addition formula we will get log y square. Now, see very carefully, this is a log function and this is an unknown function. So, when the log function will merge into the unknown function, this will create a new unknown function. So, whether we keep it log here or do not, it does not make any sense, because even then the function will remain unknown. So, it is always better to write an unknown function. So, that is why we will write g1 yx square plus x g2 yx square, where g1 and g2 are arbitrary functions. So, now let us find the particular integral, which is the solution for right hand side, and in this particular question right hand side is e to the power 3x plus 4y, and the auxiliary equation is d minus 2d dash minus 1 into d minus 2d dash. What we will do now, we will keep one factor outside and operate e to the power 3x plus 4y by another factor. Before operating, we will check that the factor which we are taking with RHS is homogeneous or not homogeneous. If it is homogeneous, we will apply the rule for homogeneous, and we already read that what is the rule for homogeneous. In that, we assume that 3x plus 4y is nothing but u, and replace d by a, d dash by b, and integrate e to the power u one time. After doing this, we will get minus 1 by 5 e to the power 3x plus 4y, and the factor outside will remain as it is. Now, we will operate the obtained function by the factor which is outside. So, we will take this factor inside, and we will get e to the power 3x plus 4y upon d minus 2d dash minus 1. So, now this is an non-homogeneous function, and for the non-homogeneous function, what do we do? How do we operate? We simply write d is equal to a, and here what is a? 3, and d dash is equal to 4. What is 4 here is nothing but b. So, what do? We replace d by a and d dash by b, which is here 3 and 4. So, we will get minus 1 by 5 within the brackets 1 upon 3 minus 8 minus 1 into e to the power 3x plus 4y, and we will get 1 by 30 e to the power 3x plus 4y. Now, since the question was in small x and small y, and for the just to obtain the solution, we have converted small x into capital X and small y into capital Y. So, the solution now again should be in small x and small y. So, what is capital X? Capital X we know is equal to log x, and what is capital Y is nothing but log y. On replacing, we will get x cube y to the power 4 upon 30. Hence, the complete solution is z is equal to cf plus pi, and this will be g yx square plus x g2 yx square. Now, how this we got? G yx square plus g2 yx square. Please see here that the complementary function was g1 yx square plus x g2 yx square. So that is why this is complementary function here, g y x square plus x g to y x square, and this is the particular integral which is 1 by 30 x cube y to the power 4, where g1 and g2 are arbitrary functions. Here we have another equation which says solve x square y minus y square t plus px minus qy is equal to log x. So now once again I will do the same thing. I will take small x is equal to e to the power capital X and small y is equal to e to the power capital Y, so that capital X becomes log x and capital Y becomes log y, and we will definitely get del upon del capital X is equal to capital D and del upon del capital Y is equal to D dash. Then the given equation reduces to this form. Now what we did in this equation, we have substituted, here we have substituted d minus 1, here I have substituted d dash minus 1, here I have substituted d, and here I have substituted d dash. So I got this equation where auxiliary equation is d square minus d dash square is equal to 0. On factorizing, we will get d plus d dash and d minus d dash is equal to 0. When we write its complementary function, once again keep it remember, the complementary function must be in terms of capital X and capital Y. Please do not write small x and small y when we are writing complementary function. So we will get f1 y plus capital Y plus capital X plus f2 capital Y minus capital X, right? Now we are on to the particular integral of the same. So this particular integral, again you know the formula of particular integral. The formula is RHS upon auxiliary equation, and we have written the same. Now please keep this remember here. This is a very important point, that log x will also be replaced by capital X. If you do this mistake, like you have reduced LHS but you forgot RHS, then it will be wrong. Right now it is correct. So please keep it remember, whenever you are reducing LHS, reduce RHS also. So in this question RHS we have capital X, and this is Pi is equal to 1 upon auxiliary equation into RHS. Again please see very carefully, this RHS is equal to x written. I can write it as that 1x plus 0y, right? That we will substitute d is equal to a and d dash is equal to b. What is a here? A is the coefficient of x and b is the coefficient of y. So a is equal to 1 and b is equal to 0. Now we will substitute it here, and how many times we will integrate? 2 times, because the order of the auxiliary equation is 2. So we will integrate it 2 times with respect to u. What is u here? U is the variable ax plus by. So what is ax plus by here? In this question ax plus by is 1x plus 0y, which is nothing but x. So it will become u is equal to nothing but capital X. On solving this, we will get 1 upon 1, we will get 1 upon 1. So this is 1 upon 1 and integral u square upon 2. I will remove this, otherwise you will get confused. So here I will get 1 into integral u square upon 2 du, because once we will integrate, then we will get u square upon 2, because the formula of integration is integral x to the power n dx is equal to x to the power n plus 1 upon n plus 1. So if n is equal to 1, we will get u square upon 2 du, and on once again integrating we will get u cube by 6. What is u? U is nothing but x, so we will get x cube by 6. Now once again, because our question was given in a small x and a small y, we have converted it into capital X and capital Y, but we always keep it remember that the solution must be in small x and small y. So, we will replace this capital Y and capital X by log y, log of small y and log of small x, and this capital Y capital X by log of small y and log of small x, and this capital X by log of small x. So, again on applying the formulas of logarithms, we will get log xy plus f2 log y upon x plus log x whole cube by 6, and we can again write it as g1 xy plus g2 y by x, g2 y by x and plus log x whole cube by 6. So, this is our answer. Thank you very much.